And here we go. Good morning, everybody. Good morning, YouTube. So just to start with our usual announcements, this is our last class. Can you believe we all made it? Well, so far. I can't believe we all made it. Anyway, so congratulations, everybody, for making it this far. Only a little bit left to go. Let's see, there's a take-home final. Just so you know, the last thing to do will be there'll be a take-home final that's due in one week. And oh, thank God, that's looking really weird. Like I said, all deadlines are elastic, so take as much time as you need. The take-home final. I have to write it. I have some idea what's going to be on, but the take-home final will be out either tomorrow, well, let's say by Wednesday, if not by tomorrow. And that will be your last assignment in the course. So, right, and problem set 11 is also, I guess I should say, also remind you also that problem set 11 is due today in principle. But again, did I mention all deadlines are flexible? Okay, and yes, and today, that's right, today is a bit of self-indulgence. Right, good morning, Apurva twice. Okay, now back to once. And so we're gonna finish up our discussion on geometric group theory that we started on Wednesday. And sit back and relax. Just let it all wash over you. If you're really gonna want to come back and study this at some point, it's all going to be preserved here and on YouTube, so you can always just go back and see the details later. Just try to take it in, soak it in. But before we get there, oh yeah, and right. And today I think, oh yes, today we'll definitely get to the part where that has some connection to what we're doing just previously with Galois theory. So we'll sort of get to the part that's my excuse for introducing geometric group theory at the end of a long chapter about Galois theory, because we'll see some connection there. Okay, so oh yes, and thanks to today's DJ Trent for picking a little Supertramp, a song from my youth. Anyway, so are there any questions before we start? And so actually, and if people have questions about Galois theory, now would be a good time to ask them, because if I don't say anything else about geometric group theory, it's not the end of the world. I mean, so are there any questions about Galois theory, about the take-home final, about assignments, anything like that? Questions? All right, I'm gonna guess that's is that Ravi coming in, or is it Mengru? Anyway, so let's get going. Good morning, new guest. Anyway, so yeah, Ravi. Okay, I guess correctly. All right, so let's get going. All right, so the whole point. So last time we introduced free groups. And we talked about the fundamental group of a graph, and we're just about to show that the fundamental group we sort of defined that. We were about to show that the fundamental group of any graph is a free group. And this is all sort of in service of proving the immediate goal is the Kurosh subgroup theorem. Every subgroup of a free group is free. We'll discuss the finite index case, and I will indicate roughly how to generalize that to the infinite index, the general case. Okay, so that's where we are. That was our goal. Still our goal from this time. All right, so let's see if we can, let's take a look at this whole slide at once. So the fundamental group of a base-pointed graph that's labeled with letters from some alphabet capital X. Oh yes, and there's a new observation. Whoa. Everybody okay? That was weird. Was that me, or was that you guys? What was that weird noise? Okay. No problem, Purva. All right. So all right, as long as it's not an unexplained weird noise, that's fine. Okay, so hello on the phone, Apurva. I guess you can watch the visual. Are you back on your laptop now? Okay, so everything's fine. All right, so oh right, you got a feedback from having both things on at the same time. Okay, very good. All right, so let gamma be a labeled graph with a base point b sub 0, and the fundamental group of gamma is written pi1 of gamma comma v sub 0 is the elements of it are reduced loops starting at v sub 0. The operation concatenation, first you do one path and then you do the next one. The identity is the empty word where you don't go anywhere, and a very familiar path for us all these days. And the inverse of a loop is, so the inverse of this loop is the same loop that gone the other way, traversed backwards. And oh yeah, and right, okay, so there's one new thing, which is that if we change the labels on gamma, right, this is an observation I didn't make last time. This is something slightly new. Well, actually, let me blow up the page just a wee bit to show that. So, so if I'll just do this all in one color just for speed. So if we have, here's v sub 0, here's maybe a couple other. I'm not gonna make this too complicated. So if I label this with a certain set of alphabets, say like one letter is called, oh geez, I guess I needed 3 there. So there's your v sub 0, and the fundamental group of this graph is, remember, it's the group of all loops starting at the base point, starting and ending at the base point. So now, oops. But now if I change, if I take this same thing, same graph, and I label it, I just decide to change all the letters, but instead, actually, you know, I'm going to label them all the same way. Oops, apparently the same way at first, but then I'm going to explain why they're actually all different. So if I take that, and instead of, and if I take that same graph, and instead of having our initial alphabet, with some of them are labeled one with 1 arrow, and some of them are labeled 2 with 2 arrows, and some of them are labeled 3 with 3 arrows. If I just pick a different letter, so to speak, well, if I just pick a different letter, not even so to speak, I'll just make it a different letter for each edge. Oops. There's D, E, F. So if I just pick a different letter for each edge, you can see that I haven't changed anything, right? Sort of combinatorially, you know, the paths that are paths in the left-hand graph, paths in the left-hand graph are also paths in the right-hand graph, and vice versa. And so so I observe that these are sort of equal, or I guess I should say pi1 of this thing equals pi1 of this thing. So I'm gonna, just to sort of make things a little less complicated in this proof that I'm about to do, I'm gonna use the sort of simplifying idea that if I just decide to label every edge with a different letter, then nothing has changed. So so does that make sense? Is that good? Fundamental group of a graph, and we can just change the labels and it's still good. Okay. All right. Now that will be at least convenient for the sake of bookkeeping in what follows. All right. So because the retract lemma. So this is what let's see. How do I speak? Oh yeah. So the retract lemma says that let X be a base pointed X labeled graph. I'm going to start to draw this as I speak. So let let gamma be a base pointed labeled graph. It's labeled with some alphabet. And let T be a tree contained in gamma. Okay, so let me, all right, so let's see. So here, I'm going to leave off the labels just to sort of make this a little faster to draw. All right, you can have multiple. Remember, you can have multiple edges. You can have self loops, and you can have multiple edges going from one thing to another. Okay, so there's a sort of random graph. Now, and let T be a tree contained in gamma. Okay, so now let me sort of make. So I'm going to pick a tree. Let's try this. I have never done this. Let's see what happens here. So I'm going to pick a subtree. Oh, that was too thick. Okay. Whoa. So it was medium thin. No, medium. Okay. So there we go. So there. So that is a subtree of gamma. So so there. So the point is, I should have just left it the same thickness. Okay. So the tree is in black, and the graph gamma here is in red. Okay, so again, let gamma be a base pointed labeled graph, and let T, capital T, be a tree contained in gamma, and let gamma prime be the base pointed labeled graph obtained by replacing T with a single vertex and giving each edge. Oops, I guess this was, so in here was our base point v sub 0, and giving each edge a different label in some alphabet y. So I'll leave off the labels. So so I'm going to make, so now I'm going to make a new tree, sort of a new graph where everything that was in T is now collapsed to a single point. And so now, do that. Okay, so so let's see. So let's see. There are there we go. There's 1, 2, 3, 4, 5, 6. Well, actually, there's not really a good way to distinguish among the 6 red edges, because now there's only one vertex. Actually, let me make this a little different. All right, okay, there, that's better. So the tree doesn't have to take up all the vertices. So now there's sort of 2 vertices, and yeah, this will be easier to sort of see what's going on here. So now there are 2 vertices. There's one which you get by collapsing everything, and there's still one red vertex left over. This is like, I don't know, V1, and now this is still V1. And now let's see. So what do you have left? So there's 1, 2, 3, 4 red edges going from V1 to the single T vertex. Oops, that's not what I wanted to do. 1, 2, 3, 4. And let's see, how many edges are there from the tree T to itself? There are, actually, let me. There's 1, 2, 3. Yep, they go from T to itself, and so this is 1, 2, up to graph isomorphism. This is what we get when we collapse the entire tree into a single point. Okay, so I did a little bit of violence here, but does that make sense? What happens there when we collapse that tree T to a single point? Good. So I guess if you want to be more formal about it, I mean, the content of what's in there is in the picture. But if you want to be more formal about it, what happens is, let's see. So you make a new graph with one vertex T, and the other vertices. Let's see, what would you formally do? You'd have a new graph where one of the vertices is just named T, and the other vertices are just all the other vertices that are not of the original graph gamma, that are not contained in the tree T. And then let's see, and then edges either any particular edge either ends or begins in T, and or ends and begins in one of the other vertices, and so there we go. I guess let me mention that you have to preserve the possibility that that there are just edges that are completely unaffected by the whole collapsing. It's just they just sort of stay the way they were. So, are there any questions about what happened there when I collapsed that tree T to a point? Okay, so then in that case, what this says, yeah, so let gamma prime be that base pointed label graph obtained by that collapse operation. Here's v sub 0. I guess it should be v sub 0 prime, strictly speaking. Yeah, it should really be v sub 0 prime. Okay, whatever. Oh yeah, and in order to sort of preserve this idea of labeling, we're just going to give every edge over here a different label, whatever. So in that case, what the theorem says is that pi 1 of gamma with base point v sub 0 is equal to pi 1 of gamma prime base point v sub 0 prime. So again, I guess it's useful to have slogans often when you have theorems, and so here's the slogan that describes this theorem: collapsing a tree to a point does not affect fundamental group. All right, so are we good about the statement of the retract lemma? Does that make sense? Oops. Okay, and and this is so. This is somehow all like for those of you who are familiar, have any sort of nodding acquaintance with topology. Somehow here we're like sneaking in some algebraic topology is basically what's happening here. But it's sort of it's disguised as combinatorics. But you would never think of this. You would never think of doing this operation just purely in terms of like combinatorics. This is really some sort of topology thing going on here. But but on the other hand, in the end, when you sort of work with this, when you actually do geometric group theory, when you work with it, you don't actually really think about the topology. You just, I mean, at least I don't. I just think about squishing little pictures. So yeah, so cartoons. This is my research life as cartoons. Okay, so let's prove this theorem. So proof of the retract lemma. So our first step is that we relabel, as we said, this is, remember, if you look back, observation, you can just change the labels on gamma, and that doesn't change the isomorphism class of the fundamental group. So we might as well label gamma, so every edge has a different label. That'll sort of remove a certain amount of complication. So so loops map to loops. We know that loops map to loops. So it'll be enough to show that one, this sort of induced homomorphism is surjective. Every loop in gamma prime is the image of some loop in gamma, and two, that this map is injective. This is how isomorphisms work, right? You got your surjective, you got your injective, and then it becomes out to be bijective. Yeah, that's how it works. All right, so my sudden lapse into Bugs Bunny aside. So yeah, so we want to show that every loop in gamma prime is the image of some loop in gamma, comes from something in gamma, and injective, a non-trivial reduced loop maps to a non-trivial reduced loop. I should say in where, huh? Non-trivial reduced loops in gamma map to non-trivial reduced loops in gamma prime. There we go. Okay, well, so everybody good with that? I guess it's only fitting that you end your year of graduate algebra with some, proving something surjective and proving that a homomorphism is surjective and proving that a homomorphism is injective. Ooh, I guess I forgot one step. Loops map to loops. I mean, it's just something that's I'll just mention, but loops map to loops, and also composite and concatenations map to concatenations. In other words, products map to products. In other words, well, I guess we had to verify that this maps, that when you sort of squish this point down, when you squish this stuff down, then that's actually a homomorphism. But I hope you can see that. I mean, a loop over here will sort of map to maybe a less interesting a loop over here. A loop over here will map to a less interesting loop over here, maybe in gamma prime, but it'll still map to loop. And if I do one path over here and followed by something else, that will produce the same effect over there. So it really is a homomorphism. So now we have to check that this homomorphism is surjective and injective. Right. This is math 221. We have a homomorphism. You want to verify that it's surjective. You want to verify that it's injective. So is everybody good on the goal? Okay. So let's do surjective. Well, surjectivity. Suppose we have a loop in gamma prime. Okay, so I'm gonna illustrate the idea using our example that we had before. So what we have here is, actually, then the color coding is not unhelpful. So right. Oh yeah, right. I should really color code this. So let's have the blue loops. The blue loops will be the loops that are unaffected by unaffected by the collapse. So they're totally the same. So now so suppose let's see. So suppose we have a path. Well, here's the picture. So what we want to do is we want to think, okay, on the one side we have a path. We start off with a path, not a path, but a loop in gamma prime. So there may be what I'm going to do instead of drawing actually the loop instead of drawing the loop inside the graph, instead of drawing the loop over here, where it could be pretty difficult to see, what I'm going to do is I'm going to sort of indicate what that path looks like schematically. And so what what will happen is that any loop in gamma it'll sort of like chase around in the blue stuff for a while, and then it'll do a red, and then it'll do a green, and green stuff, and then it'll do some red and then some blue. So remember, our color coordination is very important. So this is, let's see, actually, let me put it this way. So blue was outside, corresponds to edges that are completely outside T, and green that that those are edges that correspond to that come from edges that were completely both of whose ends are inside T, and then red edges go from T to not T. So you can imagine that a loop in gamma might have it might have some blue stuff for a while, doop, 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 and then it might transition into some red stuff, doop, oops, and then there'd be some green, doop, 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 and then it's very important to say doop, 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 and then there'd be some red again. And then there'll be some blue, and so on. Okay, so so now so does that make let me sort of repeat what's going on here is that this is sort of the blue stuff is not affected by was all among vertices that are not affected by T, and the green stuff was between vertices of T. Oops, that's not what I want to do. I want to do this. Make that green. Between vertices of T, and then the red stuff transitioned from one to the other. Okay, so so is everybody good with that picture? So does that sort of schematic make sense? That scheme make sense? Okay, everybody sort of everybody beat me to saying yes. Okay, all right. So now what we do is we pull back. We pull back. So each of those blue and red and green edges comes from so each of those blue and red and green edges comes from exactly one edge back here in gamma. So great, there's a uniquely defined pullback, and so and in fact even better, all the blue stuff sort of stays the same. So this is this because the blue stuff is not affected by T. There's no these edges are still connected back in gamma prime. Sorry, back in gamma. So this is over here back in gamma. And in fact, even because the first vertex of on this red edge, this first vertex is not affected. Was not part of T. That's still the same as it was. But now something interesting happens. All right. So now in this schematic diagram here, we have three green edges. So what happens now, though, is that those three green edges and the red edge that comes before and after them, those are not necessarily connected anymore. Right? Those are not necessarily connected anymore. And so let's see. And what else? Oh yes, and I guess let me end this with a red edge here. That's one other thing that can happen. So so what happens is when you pull back, yeah. So the basic problem that you have to worry about is that let me indicate that. Actually, let me just sort of draw it, and then I'll talk about it. So, so see the blues and the reds are still connected. But so there are two problems that sort of show up here. Oops. there are kind of two problems that show up here, and they actually end up being both fixed by the same idea. So let me indicate what's going on over here. So I need another color. So many colors. All right. So if you look at what's happening over here, let me type out in words what's happening over here. So the issue is that red, green, red paths may pull back to disconnected pieces. And similarly, a path that ends in a red edge, path that ends in a red edge in gamma prime might not return to the base point when pulled back. Right, because see, the thing is, here's the deal. Oh, I know what I should do. I should indicate, that's what I should do. What I'm going to do is I should indicate exactly where T, sort of the remnants of the sort of collapsed version of T, shows up over here. So remember the collapsed version. So the problem is whenever darn you, there we go. So whenever you have these red and green, oops, not there. Whenever you have, so remember, green edges have both their endpoints in that vertex, in that sort of collapse T, and red edges have sort of their non well, basically the point is that any green edge, or possibly one end of any red edge, must have a vertex that is in sort of the image of T. Right, there we go. Right, and so what happens is like, well, when you pull back literally just those green edges, then there's no then you might have sort of a bunch of disconnected pieces, and maybe over here, maybe I guess if your base point is in the tree, as it was in our particular example, then maybe this red edge doesn't actually end at the base point. That means, yeah, so maybe this red edge, when you pull back, sort of ends up over here, and oh no, we didn't quite get back to the base point. However, because each of these ends that we were describing is actually contained in the tree over here somewhere. So, how did I jump over there? That was weird. This is like way too fussy here. I'm sorry, I know you didn't sign up to watch me color in little points. All right, we need one more color here. Well, this is all terrible, and we have a pandemic, and it's very weird not to be able to talk to each other in person, but at least I have all the colors I want without having to use up markers. Okay, we're gonna have one more color here. So is there a gray here? Oh, yeah, there's a gray here. Right, so there. So I think I need at least one more page here. Fit page, append page. Okay, so the problem is this is no longer in gamma. We no longer have well, not only do we no longer have a loop, we don't even have a path anymore. However, note, but remember, any 2 points in a tree T are connected by a unique path within T. So we can fill all those gaps with paths from within T to get a loop starting and ending at v sub 0. At v sub 0. Let's see. I'm gonna try something I have never tried. Oh, this is extract text. So this is select. So I'm gonna. What happens if I do this? And this is. I'm just gonna be so excited if this works. So okay, we now selected this, and I'm gonna copy this, and I'm gonna click over here and paste it. Oh my God, that worked! Amaze balls. There we go. Wow, you watched me learn how to do this in real time. Okay, so basically, so what? Because each of these black endpoints is in the tree T, there is a unique path between them, somewhere in there. I mean, we don't know what it is, but we know there's something in there, and so you can sort of patch together all these little gaps, including possibly gaps at one end. And there we go. Okay, and so that's it. That's all there is. I mean, it required 4 colors to do. It's a 4-color theorem. It required 4 colors to prove that part of the theorem. So indeed, surjectivity follows. Okay, so does that make sense? So again, let me just type in a 1-sentence summary of that argument. Summary. We pull loops back and plug the holes with paths within T. So does that summary make sense? You start with a path in gamma prime, you pull it back, then you get a path with some gaps in it. And because I'm just so excited by this cut and paste thing, my world has just totally changed here. Sorry. Yeah. So right. So then we get a loop in gamma that starts and ends at the correct point. Okay. So great. So surjectivity follows. Now let's do injectivity. Right. So injectivity. Okay. Injectivity. Suppose we have a non-trivial. Well, we have. I might go back later and put in the word non-trivial there. But suppose we have a reduced loop in gamma, possibly a trivial loop, possibly just the single point. So suppose we start off with a reduced loop in gamma. So now, how could this map to a non-reduced loop in gamma prime? Let's look at the possible cases, all possible cases of consecutive edges in the loop in gamma prime. Well, okay, so what are those possible cases? Oh, I think we're gonna need one more page here. That's what I get for making this up as I go along, huh? Okay, so one possible case, for example, that's not what I wanted to do. Oops. There we go. Let's make this blue. Okay, so we could have consecutive blue edges, right? And so look at the. I mean, so all the paths in gamma kind of look like blue, red, green, red, blue, red, green, red, blue. Right. I guess sometimes the blue paths will be trivial, and sometimes the green paths will be trivial, but you sort of alternate blue and green between reds. So what are the possible consecutive edges? Well, we could have blue, 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 blue in gamma prime. So in gamma prime, that means we have this, and there are two different labels. And where does that come from? Well, that has to come from a blue, because the blue edges are completely unaffected by T. That has to come from some sort of isomorphic copy back in gamma. So this is on the left we're in gamma, on the right we're in gamma prime, and so these can't cancel because they're the same. So they can't cancel. Another possibility is we could have a blue edge next to a red edge. Oh, why is that so thick? Blue, red. What is this? Oh, I changed that. I changed the Chisley marker. Oh my goodness. That's why. Let's try that again. Blue, red. So maybe there's like a red edge and then there's a blue edge next to it. And just to make sure we don't miss anything here, one end of this is black. Well, it's supposed to be black. Right, and this is sort of sitting in the tree. I guess that's the same thing because, well, blue edges. So if they're well, I mean that's even sort of maybe more straightforward. They're sort of different color edges, so different labels. Oh, I guess so. Yeah. Let's see. So I guess we really only have to. I guess. Sorry about this. You can tell I really am making this up as I go along. My bad. But it is true that we have different color edges, so they have different labels. So I guess the same argument then works. Same argument works for green, red. So I guess now we have to worry about red, red, and green, green. Right. So let's do green, green first. So the green, green cases. All right. So suppose over here we have two green edges. Now, right, and then, so the thing we're worried about is that somehow there's a path. So let me just sort of draw your nightmare here. So maybe there are two green edges that sort of that have the same label on them, because remember this is not sort of this is I'm not drawing something literally inside gamma prime. I would thought it's sort of remember so it's a little bit tricky what I drew here. So this is mapped into gamma prime. So maybe there's some path over here in the sort of in the schematic for the path. There's something that sort of goes like bonk bonk donk in the reduced path. Yes. Right, that goes bonk donk in the gamma prime path, and this comes. So where does that? So where could that possibly come from? Well, yeah. So where does that possibly come from? So that comes from, well, what you might worry about is that you might have sort of this. So this will be like labeled A, and this will also be labeled A. Because and I guess it's reasonable to think that I didn't say that before, but I think the thing to do is sort of we can achieve different labels in gamma prime by making them all different in gamma. So right. So what you might worry about is that there's some path that sort of wanders around like this, and then this sort of starts off in A. By going in, by having an A edge that goes into the tree, and then there's some wandering around the tree somehow, and then and you leave the tree by the same by that same edge A. And so in fact, if you have this, so this is the sort of thing you have to worry about. If you actually had this situation, if you had some situation, if you were sort of collapsing some stuff over here, so this black stuff, if you're collapsing that black stuff, and there was some way to have have an edge going at A, and then you have a reduced path, and you sort of end back at the same vertex, right? Because there's only one end of A that would be going. There's a unique end of A that goes into the tree T. So this would be some vertex, I don't know, W, and this has to be the same vertex W. So if instead of collapsing a tree, so this is actually the part where we have to really use, at some point we have to use the fact that we're collapsing a tree. So if you had because we didn't actually use that in the surjectivity, we did not actually use the tree part. We just used the fact that trees are connected. They were collapsing connected graph. Here, you might have to worry about, and so in general, if you collapse something that has a loop in it, this is actually a problem. We can actually get something that's still reduced, but then is reduced over here, but then maps to something that's not reduced over there. So okay, well, that would be a problem. However, so let me remind you. Well, actually, the most important thing is that it's to understand the problem. So does that problem make sense? Problem equals possible issue. I think it's worth sort of just sort of staring at this for a second. Yeah, so let me end. So if this happened with a reduced black path, then we would lose injectivity. Yeah. Well, anyway, are there any questions about what could possibly, the thing that could possibly go wrong here? So maybe again, maybe we enter into the tree through A, and then we wander around for a while, and we come back and we exit the tree through A inverse. And so that would be if that were possible in a reduced path, then there would be then that would actually map to a non-reduced path, and then we'd have a problem. So are there any questions about that, at least for the moment? Yes, this is something. This is geometric group theory here. You have to sort of meditate about this kind of thing. Should we continue then? Okay, so that would be a problem, but fortunately, there is a unique reduced path between any 2 points in a tree, including the case where the 2 points are the same, where the 2 points are the same. So the left-hand side of that diagram, the picture in gamma is actually, so what is really going on there? What's really going on is actually this black path. Let me say that. It's actually one where the black path is trivial. Right, so there's only one reduced way to get from W to W, and it's just to sit there. And so what in actuality we have is if we just have the vertex W, and then our path back in gamma went like this. So the secret about this picture is that, so actually we didn't have a reduced path in gamma contradiction. And actually, I guess the same argument holds for red cancellation. And are we done? I guess we're done. So a reduced path. So right. Oh, there's one case left. One case left. What if we have a reduced path loop that's entirely black? Right, because the fact that we have a non-trivial image in gamma prime means that we have to have some edges that aren't black. Well, what if all the edges are black? Well, again, by the same argument, there's only one such path, namely the trivial path. So the only element of the kernel of our homomorphism is the trivial path. I think that's actually a proof. Yeah, like I said, I'm kind of making up as I go along, so that maybe wasn't the cleanest way of explaining it, but I think that's right. Okay, there we go. Oh my goodness. So that, you know, it's a hallmark of modern mathematics that if you call something a lemma, that's where all the hard work is going to be. So okay, this took some hard work. This took a little work here. So let's go back up and look at the whole thing. So the retract. Oops. Yeah. You know, I'm very fond of my laptop, the laptop that I use for classes now. I've been spending a lot of time here, but the rendering, there's some kind of problem with the rendering. Oh well. Anyway, so the retract lemma. So the retract lemma says that if we collapse a tree to a point, then the fundamental group, then we do not change the isomorphism class of the fundamental group. That's the retract lemma. So the proof is, the basic idea is you want to look at what happens. You want to show that every loop, after checking that this actually induces a homomorphism. We want to check this homomorphism both surjective and injective. So for surjectivity, you start with a loop in gamma prime, and you want to pull it back to something in gamma. Well, when you pull that loop in gamma prime, back to gamma, you get something that may not end up being a bunch of disconnected pieces. However, but because trees are connected, you can sort of fill in those gaps and get a loop again, including possibly at the end, beginning or the end, and so we're good. So that's surjectivity. Injectivity, if you have different colors. So here's how I should have started the argument. If you're in your path in gamma, you have different colors, different color edges. Those can't possibly cancel, and so the thing to worry about is the same color. Well, if you have blue, then those are unaffected by unaffected. Same isn't quite the right word here. Well, I guess those edges inject. So maybe I should say these edges inject literally, combinatorially, and so they can't cancel. I should type that out to begin with. Okay. For green, or for red. So the argument sort of, the argument really boils down to the case where you have green cancellation, exactly like this. And so what the thing you have to worry is that if you might have two unreduced edges, you might have an unreduced path in gamma prime, coming from some situation like this where you have A and then wander around in the tree somewhere for a while, and then A inverse. So if that happened with a reduced path, then we'd be in trouble. Then the injectivity would be lost. But fortunately, there's a unique. It's part of the characterization of trees that there's a unique reduced path between any 2 points in a tree, including a point in itself. And so the only way we can get this in gamma prime is if we have this back in gamma, and so which means that that really we start off with something unreduced to begin with, and so actually so that's a contradiction, so that can't actually happen. And then so the one case remaining where you actually get a loop being mapped to the trivial loop is if you have a loop that's entirely black. Well, the only entirely black reduced loop is the trivial path, and so we're done. All right, there. So any questions? Whew. Yeah, I feel like I kind of broke a sweat on that one. So that was that's what I get for making it as I go along. But I hope that made some sense. All right, so continue. We're just about to. Oh my God, we spent like 45 minutes doing that, and then we're like gonna. Oh, is there a good geometric group theory book? There's some good ones. Remind me, send me an email. There's some pretty good ones. I mean, to my taste, they just don't have enough cartoons. most geometric group theory books would sort of do this with a lot of letters. And so in the back of my mind, like sort of, I'm like writing a book right now, but I'm like, but my next book project after this is sort of like, well, I think someday I want to have geometric group theory, a graphic novel. So in other words, a comic book. So someday I want to write that or something like that. Maybe a geometric group theory picture book. I haven't quite, let's see how well I can actually learn to draw. But yeah, yeah, I don't, you know, there's a pretty good one. So actually there's a pretty good geometric group theory book. I think it's office, so something like office hours with a geometric group theorist. I think there are a lot of pictures in there. Maybe the book of mine that I did that I've been thinking about has actually been written. So maybe that's it. I haven't actually read that book, but I hear good things. But yeah, if you want to learn more about this, that's a good place. That's a good place to go. It's just that the one thing about it is that it might require you to know algebraic topology beforehand, and sort of and so because this painstaking argument here is sort of, it's a replacement for the sort of some of the hard bits of algebraic topology. You know, you have to do some work at some point, so can't completely get around it. Anyway, any other questions? So should we continue? Okay, so let's knock it out. Oh, right. So here's a, yes, but I think we'll just get to the point of the Kurosh subgroup theorem. All right. So it follows as a corollary from that lemma, right? This is sort of like modern mathematical exposition, right? You sort of do all this hard work in the lemma, and then you look like sort of nothing's happened in the corollary. That's a very so what happens as a corollary, if you have a finite base-pointed labeled graph with e edges and v vertices, then pi one of that graph is equal to Fn. That's the free group on n generators where n equals e minus v plus 1. So here's the proof. It's gonna be pretty short. Oops, let me blow this up here. Let me draw that a little better. So so if I have some random graph here, there's gamma, and then what I can do is that where can I find a tree in this thing? Well, one good place to find a tree is any edge, right? Any single edge, and that's not a self loop, right? I guess if you have either if you have more than one vertex, you have to have something that's not a self loop, and so there must be an edge that's not a self loop. So we find some random vertex, this random edge that's not a self loop, and we collapse it, so that we're guaranteed to find that as long as we have more than one vertex. So all right, so I guess I should note that if v equals 1, then we're done. So if v equals 1, then we actually have this, and we saw before, and this is actually kind of the definition of the free group, that the free group on an n leaf rows is Fn. So if v equals 1, we're done. If v is greater than 1, then there must be some edge that connects those two vertices, and so we can collapse it, and so we get something over here. Let's see. So we get donk, 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 and then donk, 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 donk. A little bit messy there. Try this. Yes. Okay. And now, yeah. So just to indicate, so as usual, this is the black vertex indicates the tree T that's been now collapsed to a single vertex T, and see, our base point stays the base point. So here's v0, little v0, and here's little v0 prime. Yeah, and so what happens now is that when we reduce E minus, we lose one edge and one vertex. So E minus V plus 1 remains constant. That's interesting, right? So, I mean, that's it. Some of you may, actually, let me, so is everyone familiar, oops. Is everyone familiar with the Euler number or Euler characteristic? How about, yeah, V minus E plus F? Does that sound familiar? So on a sphere, for example, if you have some graph on a sphere with sort of one unified outside, you get like V minus E plus F equals 2. Yeah, so this is sort of no accident that this quantity E minus V plus 1 remains constant. It's sort of this is actually the Euler. It's what you might call the Euler characteristic of a graph, and so it's not what you might call. I guess it's the negative of it actually, because you actually you want let's see, just V minus E. V minus E is Euler characteristic. Anyway, so the point is E minus V plus 1 remains constant, and so the result follows by induction on V. There we go. Ta-da! We're done. That was it. All right. Oh gosh! Oh no! We might have run out of time. Okay, so we're done, and so and let me note that it's the same is also true for infinite graphs, but you have to prove things about spanning trees of infinite graphs, and the fact to show that there is some tree that you can completely collapse to get a bunch of loops soldered together. Anyway, so let me just very quickly. How close are we? Almost. Oh no, 3 slides. Okay, let's see if I can get this done. Okay, so let's use the same, our sort of usual coloring scheme of, this is like A, and so red is going to be A, or something red like red is going to be A, and blue is going to be B. So we call a completely X labeled let's AB labeled graph a coloring space of. So what I'm going to do is I'm going to concentrate on the case n equals 2, and so there's our A, there's our B loop, and there's our A loop, and so let me see. So a covering space of the n leaf rows looks something like this. And so what I want to do, actually, this will be sort of illustrate the point of what's going on here. In order to make a covering space, I have to have a complete coloring, a completely X-labeled graph. And so one way of doing this is actually all I have to do is sort of put down a bunch of this is equivalent to actually just choosing a set of permutations that defines a transitive permutation group. Oh yeah, remember that transitive permutation group on a set of vertices. And so let me just go ahead and do that for the sake of time. Let's see, 1, 2, 3, 4. So the blue edges sort of chase around like this, And then, okay, so there, this is kind of a strange looking covering space. What's called the covering space in that, and and the reason it's called the covering space is that there's an induced map over here. There's an induced, there's a map, a graph map induced by colors and arrows. And I hope you can see what it is. All the vertices go to. Can't you still? Whoa! I do not want to do that. Yeah. So all the vertices go to the single. All the vertices up here go to the single vertex down here, and all the arrows sort of go to the directed edges in the same direction. And so if we have a covering space, we get a map, and it's actually usually that kind of map. So if you do algebraic topology, that kind of map, that's actually what's called a covering map. And so a covering space is something that does that. All right, so coset diagrams. So that's what a covering space is. So now for H in Fn, we define the right, and again, I'm just going to stick with the case n equals 2. We define the right coset diagram of H to be the base point at X labeled graph, the AB labeled graph given by, well, if you have a coset HA, oops, I shouldn't call it HA because I have A and B are dedicated generators. Oops, I almost threw away our document. That would have been very bad. So here's, so let's call this HX. So what you have, if you have this edge labeled A, there's always, for any HX, for any, I guess I should say, little g in Fn, if I have the coset Hg, and there's always going to be some edge for any letter of the alphabet, little a and big X, there's going to be some edge coming out of Hg. It's going to go from Hg to Hga. And similarly, there's going to be, oh my gosh. All right. I should not go over time on the last day. So I'm just going to sketch out what happens here. But anyway, so similarly, there's going to be an edge starting at Hg and that ends at Hgb. And so these are all right cosets. So this gives a graph. This gives a completely X labeled graph whose vertices are the right cosets of H. So that's called that's what you call the coset diagram on the generators in X. Okay, so so in 2 sentences, terrible. Okay, and so let me just sort of state the coverage. And so here is finally is the excuse. Well, it all kind of finally goes back to Galois theory. There's some connection. What we have here, so what happens with covering spaces like these things, is that there is actually what a Galois correspondence. So that so yes, there was an excuse for doing this. There really is a Galois correspondence, which says, again, always have to be base pointed covering spaces. A Galois correspondence says, if base pointed, so here's how the Galois correspondence goes for covering spaces. Given a subgroup H, you map that to its base pointed coset diagram. And again, you always want the base point of a coset diagram has a very natural base point. The base point is the coset H itself, or H time. Well, yeah, the trivial coset, the coset that's actually a subgroup. So if you map H to its coset diagram, and conversely taking taking a covering space gamma v sub 0 to its fundamental group, that ends up being a Galois correspondence. So again, so this is not going to be a proof even. This is just going to be a sketch. So again, H maps to the coset diagram with base point H. And conversely, if you have a base pointed covering space, a gamma and v sub 0, you can check that this and you define a map that goes from that graph to its fundamental group, then this is a bijection. And you can check, oops, and you can check that these are inverses of each other. Check these maps are inverses of each other. Which we would, actually, I totally would spend a little time doing here if we didn't have -1 minutes left. My bad for chilling out at the beginning. So proof of the Kurosh subgroup theorem. Well, and here's how it goes. It's actually pretty short at this point, I think. Let H be a subgroup of finite index. Why did I leave a whole page for this? Index in Fn by the correspondence of covering spaces. H is isomorphic to the fundamental group of a graph, which we showed must be a free group. Huh. Yeah, somehow, that wasn't exactly what I planned, but I think it's kind of cool that it turns out to be a 2-sentence proof that we fit into 1 minute. All right, well, I think it's a fitting end of the semester. Not entirely planned, kind of running over time and a little bit chaotic at the end, but I hope you enjoyed that. I think it's not a bad note to go out on. Thank you for being a very patient and wonderful class. It's really been a great honor and a pleasure teaching you. We still got another week to go. Got another week of work to do. I'll be in touch. But it's been an honor and a pleasure and a great joy. So thanks very much. Bye.
Bye.
Thank you, Dr. Shu.
I should